Alrighty folks, so it's time for another problem session. This is week 5, at least of these problem sessions. I'm going to go ahead and keep them numbered in order, just skipping the week where we had an exam instead of one of these, rather than skipping a number, just because that seems to make the most sense to me. Hopefully it'll be pretty clear to y'all guys. So most of our problems today come from the homework. So we'll hop in with those first. So like number 2 from the homework this week. And that said something like use the limit definition of the derivative to find the slope of the tangent line to the curve f of x equals 3x squared at x equals 5. Right? So first off, we want to make sure we understand what all is in this problem. So the limit definition of the derivative means that we're going to be using f prime of a equals the limit as x goes to a of f of x minus f of a all over x minus a, or the limit as h goes to 0 of f of a plus h minus f of a all over h. Right? Either of those are the limit definition of the derivative. And that comes into play here because the slope of the tangent line to f of x at x equals 5, right? So this piece is asking us to find f prime of 5. All right, so the slope of the tangent line is to a function is always given as the derivative of that function, and then this part of the statement tells you what you're plugging into the derivative. Right, so the slope isn't the function derivative. The slope is the derivative values. You're never going to have x as part of your slope. That's a mistake that comes up fairly often when we get to this point of things in a calc class. But the slope of the tangent line is f prime of a, so f prime of a specific value. It's never f prime of x. That's not your slope, right? So, but we have a value to plug in. We know we want to plug in 5. So we need to use one of these two definitions where a is equal to 5, and that will give us the slope of the tangent line. Which one we choose doesn't really matter. I'm going to choose the first one just for fun. So if we put these two guys together, we get that f prime of 5, which is the slope of the tangent line, to f at 5 is equal to the limit as x goes to 5, because that's what we're plugging in here. Right, so all those places are going to be replaced. F of x minus f of 5 all over x minus 5. Now, obviously, that's going to be an indeterminate form. F of 5 minus f of 5 is always 0, and 5 minus 5 is also always 0. And in fact, with the limit definition of the derivative, you don't really need to check for that. It's always going to be an indeterminate form when you first look at it, right? So you can go ahead and hop into dealing with it algebraically, right? And to do that, we need to plug in. So f of x is just 3x squared. F of 5 is 3 times 5 squared all over x minus 5. Now, our primary way of dealing with indeterminate limits algebraically is to factor, right? And so there's one easy factor that we can see up top there. The bottom, there's not really anything we can do. It's about as factored as it comes. But we can pull a 3 out up top, And then we notice that the rest of the top is a difference of squares, right? So that's another thing that's pretty easy to factor once we get that 3 out of the way. The difference of two things squared is the difference of the two things times the sum of the two things, x minus 5. The two factors cancel out, and we're left with the limit as x goes to 5 of 3 times x plus 5. Now, we've gotten rid of any denominator, so there's not going to be an indeterminate form, and we can just say this is, oops, don't need a limit anymore, 3 times 5 plus 5. We can use substitution, because this is just a polynomial, and we get 30. So that's going to be what it's asking for. That's the slope of the tangent line to that function at x equals 5. All right. So next up is very similar, except it wants us to go a step forward, or a step further, rather. It says let f of x equal the square root of 10 minus x, and says compute the derivative at 3, so f prime of 3, using the limit definition. All right, so we specifically want to do it that way again. And find the equation for probably the tangent line at x equals 3. Right? So, again, limit definition, we're familiar with that from what was up above. The tangent line at x, right, we have a formula for that. That's always going to be y minus f of 3, right, because of this guy, equals f prime of 3, that's the slope, times x minus 3, right? And again, all of these 3's come from this statement here, right? So once we find f prime of 3, we can also find f of 3. We can plug both those into this formula, and then because of what the computer is asking for, we need to solve it for y. Right? If you're doing this for an exam or for me or something, I wouldn't mind if you left it in this form. Point-slope form is just as good as slope-intercept form. But the computer needs to know exactly what to look for. It can't distinguish between the two. So you'll note on the problem, the second half of the question says y equals, and then it has a box for you to put in your stuff. Right? So that means that in order for the computer to understand your question, you first need to solve this for y, and then put whatever's on the other side of the equal sign into the input box. Right? So this is perfectly fine in general. The only reason we're going to be solving for y is because the computer needs us to be specific for it. Right? So, but first off, we need to do what it says first and compute f prime of 3 using the limit definition. This time I'm going to use the other formula for it, just to have the widest range of examples. Again, it doesn't matter which one of these you choose. Whichever one you're more comfortable with is fine. Right, so again, we know that this is guaranteed to be an indeterminate form, so we're going to need to do some algebra for it. F of 3 plus h is going to be the square root of 10 minus, and here's where we have to be careful, 3 plus h. Right, it's not minus 3 plus h, it's minus the entire quantity 3 plus h. Right, minus f of 3. It's going to be the square root of 10 minus 3 all over h. So if we do our basic simplification here, we get the square root of 7 minus h note, because this negative has to go to both pieces here. Right? Minus the square root of 7 all over h. Right? So, usually if we're trying to simplify an indeterminate form algebraically, we try to factor things. It's really hard to factor something with that square root in it. So what we're going to do is we're going to try to get rid of the square root stuff up top. Right? And the way we have to do that is multiplying by the conjugate. And if we're going to multiply by something, we've got to do it on the top and bottom so that we're not changing anything. Right? And we remember that this is okay. It means we're going to have this square root stuff on the bottom, but it's going to be square root stuff that's not going to 0, so it's not square root stuff that we're going to have to factor. Right? So the reason we multiply by the conjugate is it makes that multiplication really easy. Right? It's going to give us the square of these two pieces, which the square of a square root is really just those guys, minus the square of these pieces. Again, the square of a square is just, or the square of a square root is just what's inside. So we get the limit as h goes to 0. 7 minus 7 cancels each other out. There we go. Make sure it looks like a minus there. That one's a plus, though. And now, this h that's a factor of the bottom and this h that's a factor of the top can cancel out. And we get negative 1 up top. Square root of 7 minus h plus square root of 7. And now, we can do our substituting thing. Substituting gets us negative 1 over the square root of 7 plus the square root of 7. So that's negative 1 over 2 square roots of 7. Right, so that was the answer to the first part of this problem, which was to compute f prime of 3. Now we need to find the equation for the tangent line, so we need y minus f of 3. We actually already figured that out, right? This is f of 3. And then that's going to equal f prime of 3 times x minus 3. Right, and if we solve for y, that just means adding that square root to the other side. Lots of times we want to simplify this by multiplying through. It doesn't actually help us in this case, but if you feel more comfortable with it, this is another way to write out that thing. The computer should accept this guy, though. So there we go. We have computed f prime of 3, and then we found the equation for the tangent line and solved it for y, so that we could fulfill the details of what the question asked. Right. Alrighty. So, next up we had a question about number 4. I'm just going to check. Okay, good. Given g of x equals 5 over x plus 6, evaluate and simplify g of negative 3 plus h minus g of negative 3 all over h. So one thing to notice there is that's the difference quotient, right? Or that's one form of the difference quotient. That's the thing that if we were trying to find g prime of negative 3, If we took the limit of this guy as h went to 0, we'd get g prime of -3, right? That's why this sort of algebra problem is here in the middle of this homework, is because that's just a difference quotient. That's just practice for helping when we need to use the limit definition to find the derivative. So g of -3 plus h is 5 over -3 plus h plus 6, right? Because we take whatever's inside there and replace x with it, minus 5 over -3 plus 6 all over h. Now, just to simplify things real quick, this becomes h plus 3 on the bottom, and this just becomes 3. And so there are a couple of different ways you could deal with this at this point. One is that you could just try to get rid of the small denominators, right? When we look at this fraction, we have this big denominator, and then we have these small fractions that have these small denominators, right? So one of the ways to do this is to multiply by 3 times h plus 3 on the top and bottom, right? So this is one option, is to multiply by that. The other is to notice that dividing by h is the same thing as multiplying by 1 times h, right? And then we can distribute, right? So, right, over here, this method involves getting rid of the small fractions, right, these guys here, and keeping the big fraction. This method involves getting rid of the big fraction and just keeping the two small fractions, right? They're both going to get you exactly to the same place. It's just a slightly different algebraic path. All right, so what we want to do here to simplify is we want to get a common denominator, right? So one thing we notice is that this has a factor of h and a factor of h plus 3. This has a factor of 3 and a factor of h. So each one of these two denominators is only missing one factor, right? They both have this factor of h, so that's good. But this one on the right needs a factor of 3 added, which we can add just by giving that factor to the top as well. And then the one on the left needs this factor of h plus 3 added, so we get 3h, h plus 3. Right? Now that they have a common denominator, we can say this is 15 minus 5 times h plus 3 all over 3h, h plus 3. And now I need to get, if I'm going to cancel something out, which, given that I know where this comes from, I should be pretty well aware that we want to cancel something out, probably that h, right? We've got to do that. We got to have the top be in factored form, right? The top is not factored. It's a pair of, it's a sum, or rather a difference of things that are factored. But the top itself is not factored, and we can only cancel out factors. So we need to multiply that -5 through. We get minus 5h minus 3 times 5 all over 3h, h plus 3. 15 and minus 15 cancel each other out, so we've got -5h, 3h, h plus 3. Now this h is a factor and this h is a factor, so we get -5 over 3h plus 3. And there's not really anything we can do to simplify that guy. Right? So that's going to be our final answer once we evaluated that difference quotient and then simplified it as much as we could. Right? And again, keeping in mind where this comes from, the idea is we want to now take the limit as h goes to 0, not for this problem, But usually this is why we'd be doing something like this. And that limit is perfectly fine to take of this guy, right? That's sort of our indication that we've definitely simplified enough, is that we would be able to take this limit now if it were that kind of problem. Right? Okay, so next up is someone asked to do one like number 6. And that said, if f of x was something along these lines, right, then find f prime of x. So one thing to note here is that this problem does not say use the limit definition to find it. So please don't use the limit definition. I don't want to use the limit definition. That sounds horrible and awful, and I don't want to do it. Right? So, but since we're just asked to find the derivative, we're not told how to do it, we can use our rules. Right? And one thing that's very nice to note about this problem is that it is just a sum of power functions. They're weird looking power functions. They're weird powers, but the power rule for derivatives doesn't care how weird your power is, right? So f of x is that guy, right? We can write this as 12 times x to the 2/3, right? That's what the third root and the square turn into. And this is 7 times x to the -6 times x to the -1/2. Right? We can turn this dividing by a power function into just a power function using negative powers. Right? Which means we don't have to use the quotient rule, and anytime we don't have to use the quotient rule is good by me. Right? So, and when we multiply two exponential expressions with the same base together, we can add their powers. So 1 plus 2/3 is 5/3. And -6 plus -1/2 is -13/2. Right? Now we can just use the power rule. So f prime of x, we can pull that constant out. We bring this power down. So 12 times 5/3. And then we take that power and we subtract 1 from it. So we get 2/3 out of it. We take the 7 and we pull it out front. We bring that power down to multiply it. And then we subtract 1 from that power. So that becomes -15/2. All right, so the 12 and the 3 cancel out to make a 4. So we get 20x to the 2/3 here, plus, whoops, it's going to wind up being minus, right, because that negative is going to get pulled out front. 7 times 13 is 91 over 2, x to the -15/2. And then if we really wanted to, we could translate this back so it looks more like what we started with, right? That x to the 2/3 becomes the cube root of x squared. The negative power means that this goes to the denominator and becomes positive. And 15/2 is 7.5. So that's x to the 7 times the square root of x. Right, but this would also be a perfectly fine way to leave the answer as far as I'm concerned. If the program winds up not liking it, just let me know and I'll fix it. But it should accept something that looks like this. Right? Alrighty. Next up, I believe our questions skip to, let me make it clear that it's like number 10. So anytime that pops up, I get paranoid. So that one says use the quotient rule to find the derivative of 6e to the x plus 17 all over 3x cubed minus 10x6. So this one came along with some instructions. One was just a reminder, right? When you type in, if you want to do e to the x, right, you type in e caret x, right? That's just how you do powers just in general. And the other instruction was you don't need to expand out your answer, and we'll talk more about that at the end, right? That's giving you instructions on how to input it. So once we get to an answer, I'll tell you when we can stop and what it means by that. Right? So it does tell us right off the bat that we're going to be using the quotient rule. And remember, the quotient rule is the one that splits your function up into a low and a high. Right? So the low here is 3x cubed minus 10x6. And the high is 6e to the x plus 17. And you need to know the derivatives of each of those pieces in particular. So d low, we're going to use the power rule. We're going to bring that power down, multiply it by the 3, and subtract 1 from it. Then we're going to do the same for this power function. So we bring that 6 down and multiply 1 from it. Then we also need the derivative of the high. That one's pretty easy. The 6 is just a constant, so we pull it out. The derivative of e to the x is always e to the x. Just always is. And the derivative of constants goes away. Right? So we have our low, we have our high, we have the derivative of the low, we have the derivative of the high. And then we remember that the quotient rule is low d high minus high d low over the square of low we go. Right? And so now we get to don't need to expand out your answer. Expanding out an algebraic function that looks like this means getting rid of all the parentheses, right? It means distributing this guy, it means foiling this guy, and it means foiling this guy. Right, because secretly there's another copy of it. So that's what expanding means in general in math. If you're expanding an algebraic expression, you're getting rid of all the parentheses and multiplying everything out. So what this problem is saying is don't do that. It's saying that this right here, with its parentheses and its multiple pieces, and its factor denominator, that's what it wants as a final answer. Don't try to multiply it out. Don't deal with whatever algebraic shenanigans can show up there. Just put this whole thing, parentheses included, as your final answer. Do be careful about the parentheses. Make sure they show up all right. But putting it in there with the parentheses is what this part of the instructions means. Right. Next up, we had a request for like number 11. All right, so that one said if f of x is equal to the square root of x minus e over the square root of x plus e, then find f prime of x and f prime of 9. Right, so this was similar to what problem was that? That was, well, wasn't really similar like any of the ones we've done today. But, again, I guess similar to what we've done these past couple times, number 6 and number 10, we don't need to use the limit definition, right? We also do need to use the quotient rule, right? Because it's a quotient. It didn't explicitly tell us to, but when we got a quotient, it's sort of our tool on the table now. We haven't done quotient rule yet, or we haven't done chain rule yet, rather. We've definitely done quotient rule, but we haven't done chain rule, so we don't have a way to work around it. So that means we need to figure out low and high again. So low is the denominator, high is the numerator. We need to take the derivative of each of those again. The square root of x is just a power function, with the power being 1/2 again. Recall this is x to the 1/2 plus e. This is x to the 1/2 minus e. So we're going to get 1/2 x to the negative 1/2, right? Because we bring that 1/2 power down and then we subtract 1 from it. And e is just a constant, right? E is a number. And so when we take the derivative of it, it becomes 0. D high is actually going to be the exact same thing, right? Because we take the derivative of the square root of x, we bring that 1/2 power down, and we subtract 1 from 1/2 to get negative 1/2. And negative e is also just a number. So when we take the derivative of it, we get 0 again. Right? So f prime of x is equal to low d high, right? And I'm actually going to go ahead and write this as 1/2 times the square root of x. 1/2 times the square root of x, because I think it'll be helpful in simplifying. So low d high minus high d low over the square of low we go. And we can simplify this a little bit, right? When I multiply this through, I get 1/2 plus e over 2 square roots of x, right? Minus, multiply this through, I get 1/2, right? So we got to multiply both pieces through. So these two negatives cancel out and give us a plus e over 2 square roots x all over this guy. Can't really be any more simpler than factored form like this. The 1/2s cancel, and when you add these two together, you get 2e over 2 square roots x all over square root of x plus e squared. Right, so the 2's cancel. And I'm going to use that trick that we used with the h's above in problem, what was it, 4? No, not 4. What problem was it? No, it was 4. I'm just misreading something. So if we divide by that, that's the same as multiplying by 1 over that. So this becomes e over the square root of x times the square root of x plus e squared. So that's about as simplified as we can make this guy. There's no factors that we can cancel. Everything's all completely factored out. So this is a good final answer for f prime of x. And f prime of 9 is going to be e over the square root of 9 times the square root of 9 plus e squared. All right, so this would be our final answer for f prime of 9. All right. Alrighty. So the last one from the homework is the very last one on the homework. And it says if f of x equals 3x cubed plus 7x squared minus 2x plus 11 divided by square root of x, then find f prime of x and f prime of 1. Right? So we could use the quotient rule here, right? It's definitely a quotient. There's a polynomial up top and a square root on the bottom, and we could absolutely use the quotient rule. Or we could simplify f before we take the derivative to make our lives a little bit easier. So that would be my suggestion for this guy, right? Because when you have a sum up top and a single term on the bottom, you can split that up like this, where that single term gets divided by all the terms that you have up top, right? Which may seem like we just made it more complicated, except each of these terms now is a power function, kind of like what we had on problem number 6, right? So this is 3 times x to the 2.5, right, plus 7 times x to the 1.5 minus 2 times x to the 0.5 plus 11 times x to the negative 0.5. Right? And you could do fractions there as well, right? 5 halves or 3 halves or 1 half. Right? I don't have a particular reason why I chose to do it in decimal form this time. It just is, I guess, what I did. Right? So now we have a series of, a sum of power functions, and we can just use the power rule instead of the quotient rule. Right? So f prime of x becomes 3 times 2.5 times x to the 1.5, right? We bring this down and we subtract 1 from it. This becomes 7 times 1.5 times x to the 0.5. This becomes minus 2. And let me not use that dot. That's not great notation. Times 0.5 times x to the negative 0.5 plus 11 times negative 0.5 times x to the negative 1.5, right? Every time we brought the power down, and then we subtracted 1 from it. Right, so this is 7.5 times x to the 1.5 plus 10.5 times x to the 0.5 minus 2 and 0.5 multiply together to get 1. So I can leave that off. This negative comes out, so it's subtraction instead. Half of 11 is 5.5. Okay. So that would be our derivative. And it also asked for f prime of 1. That just means plugging 1 in for everything. And so we get 11.5. Right. Alrighty, you could also, again, use the quotient rule if you wanted. Low would be the square root of x. High would be 3x cubed. I'm not going to have enough room for it there. There we go. That's better. And then you could find d low and d high. That wouldn't be too hard. Then you plug it into the formula, and then you'd have a bit of simplifying to do, right? It's not going to be the worst. It's never going to involve FOIL. You're just going to have to distribute either low or d low. So it's not that much extra work. It's just I tend to prefer to avoid the quotient rule when I can. Right? So There's one more problem, and I think I can fit it here. We're gonna try. Maybe I'll get, maybe I'll fly too close to the sun, and there'll be some hubris. But this was from section 3.5, number 33, and it wanted a general form of the nth derivative of x with f of x equals x to the negative 1/2. Right, so what you want to do for problems like this is try to find a pattern. So f prime of x is going to be negative 1/2 x to the negative 3/2. F double prime of x, we're going to use the power rule again, so we're going to get positive 3 this time. And I'm just going to note that this is 2 squared rather than multiplying it out. It's often a good idea when you're trying to find a general form of these things is to not multiply everything out, not simplify everything out as much as you can, because that might help find the pattern. All right, so I'm going to do the same thing for f triple prime of x, right? It's going to be negative again. We're going to have 3 times 5 up top, 2 cubed down below, and it's going to be x to the negative 7/2. And I'm going to do one more just for the pattern's sake. So it's going to become positive again. We're going to have 3 times 5 times 7 up top, all over 2 to the 4, x to the negative 9/2. Right, so this is when n equals 1, this is when n equals 2, this is when n equals 3, and this is when n equals 4. Right, so one thing that seems to be happening is that it is negative when n is odd, and it is positive when n is even, right? And another thing that has that same form is negative 1 to the n, right? Negative 1 to the n is always going to be negative if n is odd, and it's always going to be positive 1 when n is even, right? So it's not actually changing the numbers involved, it's just swapping between negative and positive like we want. The other thing that seems pretty obvious is that the denominator is always 2 to the n, right? 2 to the 1, 2 squared, 2 cubed, 2 fourth. So the bottom is always 2 to the n, right? So one of the nice things to know when you're doing something like this, specifically for this problem, is that odd numbers always look like 2n plus 1 or 2n minus 1. Every single odd number can be written that way, right? And so the other thing we notice is that the numerator of the power on x, we're going to need some stuff up here, so I'll leave space. But the numerator of the power on x is always an odd number. It's always a negative odd number. Right, so it's always negative, it's always odd. So is it 2n plus 1 or 2n minus 1? Right, well, when n is 1, we get 3, which we get 3 when we plug 1 into here. When we plug 2 into here, we get 5. When we plug 3 into here, we get 7. And when we plug 4 into here, we get 9. So it looks like this power is negative 2n plus 1 over 2. Right, so that means that we match up at least with the 4 we got here. And it seems like the pattern will continue. And the thing up top is a little bit trickier. There's no neat way of writing it, right? But we know that we start with multiplying by 1. All of these are going to be multiplied by 3. That 3 is going to stick around. But then we do all of the odd numbers up to a certain point, right? So 1, 3, 5, 1, 3, 5, 7. The next one, even without doing it, we can tell is going to be 1, 3, 5, 7, 9. So we know that this is going to be all the odd numbers. So again, we need something that looks like this or this, right? But here, we stop at 1 when n is 1, right? Which means we should be looking at this guy. When we plug 2 into 2n minus 1, we get 3, and that's where we stop here. When we plug 3 into 2n minus 1, we get 5, and that's where we stop here. So it looks like we're always going to stop at 2n minus 1, right? So we get to use both formulas for odd numbers in this problem. So our formula, there we go. Our formula for the nth derivative is going to look like this. Right? So it bounces between odd and even. It multiplies up all the odd numbers up to a certain point. There's always n 2's on the bottom, right? Because every derivative is going to get us another 2 from here. There's always a 2 on the bottom of the power, and the power is going to go down by odd numbers, right? So that would be how we get the general form of f of n for that function, right? Alrighty, so that is all of the questions that were asked on the discussion board. As a reminder, if anybody's watching these who's not actually doing that part of their homework that is for a grade, you need to do them on time. Doing them late doesn't count because it's participation points. So, just in case you're watching this and aren't actually requesting things, you do need to start requesting problems. But I'll see everybody next week. Yeah.